Good morning, sir. I am K. Vanilla. My roll number 25955886626. I am from CSC Department of AML D section, and my course title is the Computer Networks, and my topic title is an asynchronous transfer protocol for quantum data networks. We can go through this. Introduction to quantum data networks. The quantum data networks or the leverage quantum interarrangement and super to the enable secure and high-speed information transfer across distributed nodes. And unlike the classical networks, the QDNs transmit qubits encoded in quantum states such as photon polarization or spin and requiring fundamentally different transport mechanisms. And next, the no cloning theorem prevents qubit duplication and making traditional retransmission based error recovery infeasible in quantum communication. And the quantum channels exhibit high sensitivity to decoherence and noise, the necessitating protocols that minimize latency and maximize fidelity. And next, this presentation introduces an asynchronous transport protocol designed to handle the unique constraints of quantum information flow in networked environments. And this is the quantum data networks that transmit qubits encoded in quantum states, and it can prevent qubit duplications and it can make traditional transmissions based error recovery infeasible in quantum communications. That can minimize latency and it can maximize fidelity, and this can necessitate the protocols that can minimize latency and it can exhibit high sensitivity. And next, we can go through these the challenges in quantum transport. The challenges are the first one, the decoherence limits qubit lifetime and requiring transport protocol to operate with the coherence time thresholds that typically microseconds to milliseconds. And next, the entanglement distribution is probabilistic and suffers from exponential loss over distance due to photon absorption in fiber or free space. And next, the quantum measurements collapse states, preventing acknowledgement based feedback loops used in classical TCP/IP protocols. The asynchronous arrival of entangled qubits at receivers demand buffering mechanisms that preserve quantum superposition without measurement. And next one is that the network topology dynamics and node mobility introduce timing uncertainties that disturb the synchronized quantum operations. These are the challenges in the quantum transport that it can decoherence limits qubit lifetime and they can form the exponential loss over distance that due to the photon absorption in fiber or free space, and it can collapse states and it can prevent acknowledgement based feedback loops using the TCP/IP protocols, the transfer control protocols and interference protocols, and these asynchronous arrivals of entangled qubits receives demanding buffering mechanisms, and the network topology dynamics and node mobility introduce the timing uncertainties that which can disrupt the synchronized quantum operations. And next, asynchronous protocol design principle. We can go through these the protocol design principles. The first one is the protocol employs event-driven state machines to manage qubit transmission, reception, and entanglement swapping without global clock synchronization. And next, it uses quantum timestamps encoded in ancillary qubits to track causality and ordering across distributed quantum processors. And next, the flow control is implemented via quantum ready sliding windows that adopt based on measured channel fidelity and decoherence rates. And the next one is the error handling. The error handling relies on quantum error correcting codes, example surface codes that can which integrated into packet headers rather than retransmissions. And next, the design supports out of order delivery by maintaining quantum buffers with coherence, preserving storage using dynamical decoupling techniques. These are the protocol design principle that uses the quantum time steps, and it can control the flow control is implemented via quantum ready slidings, and it can error handling relies on quantum error correcting codes, and these protocols can design supports out of order delivery by maintaining quantum buffers with the coherences, and the protocols employs are event driven state machines that can manage qubit transmissions, and it can entanglement the swapping. And next, the quantum packet structure. Each quantum packet contains a header with classical metadata that are sources, data, sequence ID, that and a payload of one or more encoded qubits. And the header includes a quantum checksum derived from stabilizer measurements of the payload's logical qubit states. And next, the entanglement flags indicate whether the packet participates in a distributed well state for teleportation based transport. And next, the timing metadata uses a hybrid classical quantum timestamps that are CQTs, and it can combining the classical UTC with quantum phase references. And next, the optional ancillary qubits are included for real-time errors syndrome detection without collapsing the primary data qubits. And this is about the quantum packet structure, that each packet contains a header with classical metadata, and the header includes a quantum checksum, and the entanglement flags indicate whether the packet participates in a distributed well state. And next, the timing metadata uses a hybrid classical quantum timestamps, and the optionally ancillary qubits are included for real-time errors syndrome detection without collapsing the primary data qubits. And next, entanglement-based transport mechanisms. The protocol uses quantum teleportation to transmit qubits that sender and receiver that share entangled bail pairs established via entanglement swapping across intermediate nodes. And next, the transmission is initiated by performing a Bell state measurements on the source qubit and one half of an entangled pair that collapsing the state. And next, the BSM outcome is sent classically to the receiver, who applies a corresponding Pauli correction that I, X, Y, Z, that are the two used to reconstruct the original qubit. And next, the success probability of teleportation is 1 for ideal channels but degrades with entanglement fidelity F, yielding effective throughput theta equal to F into R, where R is the raw rate. And the next is asynchrony is managed by queuing BSM results and applying corrections in casual order using quantum time step settings. This is the entanglement based transport mechanisms. And next, the asynchronous acknowledgement scheme. Instead of classical ACKs, the protocol uses quantum non-demolitions measurements to verify successful reception without collapsing data qubits. And next, acknowledgement is encoded in a separate entangled photon streams where detection confirms delivery via coincidence counting. And next, the ACK qubit is teleported back to the sender using a reverse entanglement channel, and it can preserving the quantum coherences. Next, the timeout mechanisms are based on expected decoherence time T2 with the retransmission triggered if no Q&A ACK is received within T less than 0.8 less than T2. And next, cumulative acknowledgements are aggregated using quantum superposition of ACK states, reducing classical overhead in multi-packet flows. These are the asynchronous acknowledgement schemes, and these can be classical ACKs, and this is encoded in a separate entangled photon streams, and the qubit is teleported back to the sender using a reverse entanglement, and the timeout mechanisms are based on expected decoherences time, and these can are aggregated using quantum superpositions. And next, flow and congestion control. Congestion is detected via monitoring of entanglement generation rate and the loss rate across network lines, and the protocol adjusts transmission rate using a quantum adapted additive increase and multiplicative decreases. And next, the flow control uses quantum window sizing, and they can ensure packets are sent within coherence bounds. And the periodic queuing is implemented using quantum superposition of packet states and allowing parallel processing of high priority qubits. And next, the back pressure signaling is achieved through entanglement reservation request and where nodes broadcast available bail pair capacity. And the error detection and correction. The errors are detected using stabilizer measurements from surface code patcher to embedded in each quantum packet's logical qubits. And the syndrome extraction is performed via ancillary qubits measured in X and Z bases without disturbing the encoded data. And the persistent errors trigger fallback to entanglement distillation protocols, example BBPSW2, that are used to purify degraded bale pairs, and they can correct the applies logical poly operators based on syndrome decoding using minimum weight matching. And next, timing and synchronization. Asynchronous operation relies on quantum timestamps, and this casual ordering is enforced using a quantum version of Lamport clocks, where each event increments a qubit-based counter in superposition. And the protocol tolerates clock skew up to Tmax to T coherence by 10 to prevent state misalignments during teleportations, and the time bin encoding allows multiplexing of timing and data information on a single photon, and it can use to reduce the channel overhead. This is the timing and synchronization. And next, the security considerations. The protocol inherits quantum security from entanglement based key distributions, and it can eavesdrop attempts to disturb quantum states. And authentication uses quantum digital signatures based on symmetric key hashing of qubit sequences with one-time use. Denial of surfaces attacks are mitigated by rate limiting entanglements requests, and the forward secrecy is ensured by frequent rekeying via quantum key distributions, and it can be divided to sessions triggered after every n packets. And performance matrices and analysis. This is a throughput is defined as equal to n success, and this is the formula. And latency includes entanglement setup, and the fidelity measures closeness of received state, and the scalability is analyzed via entanglement generation rate scaling as order of n square for n nodes, and the simulation results show 85% fidelity over 50 km fiber with 10 Mbps classical channels and 1 kHz entanglement rate. These are the future work and research directions. Integration with quantum internet architectures such as the quantum internet interference model is underway, and the machine learning techniques are being explored to predict decoherence patterns and dynamically adjust transmission parameters. And these are the development of hardware efficient quantum buffers using rare earth dropped crystals aims to extend coherence times beyond 1 second. And the standardization efforts are targeting IETF like frameworks for quantum transport layer protocols in next generation networks. Thank you.